Hello viewers, welcome back to another adventure of live coding in a high-level language for a low-level target. This time we're going to be working with Risc-V, which has become a much discussed architecture in the last few years. I've been looking at it from my perspective as a decompiler author, and I'm really attracted by its very nice instruction set architecture, which is easily decoded and nice and regular. And so I thought, why not make a fun exercise and write an emulator for this beast. I don't have a Risc-V device at home, but I can write an emulator, and that would be tantamount to the same thing. So let's start writing a Risc-V emulator. But before I start coding, I wanted to make a note that this video is intended as a tutorial for people who may be new to machine code and assembly language programming. And so I'm going to start it a little slow, and then as I go through the material, I will pick up some speed, and eventually I hope to be demonstrating some things that might be interesting to people who have had experience with assembly language program before. Now the approach I'm going to be taking is one that I haven't seen in the wild, but which I thought might be an interesting take, which is to reverse the process of the way that programming has evolved over the last 80 or so years. And I'm going to be starting at a high-level language like C# and then working my way down to the machine. And I'm hoping that this might give some interesting insights for those of you who are not that familiar with low-level programming like machine language or assembly language. So, well, let's get started. So I have here a completely empty C# project, and I'm going to start coding in this very simple little program that we'll be using as a test case for this emulator business. So forgetting about emulation and Risc-V for the moment, let's just write a simple C program or C# program that computes something very trivial. So we'll start with a bunch of variables. We'll give them some initial values, and then we'll have the program, which will compute a result based on let's say times 3 plus b times c minus 1. And then we're going to print out the result on the screen. Alright, so here's our little program. Very trivial. You could imagine this being written in any other high-level language like Python or your favorite, Java, what have you. Now let's try executing this and see what value we get. Ooh, we get 0. Does that make sense? 8 times 3 is 9. Minus 8 minus 1 is 0. So by sheer accident, I managed to write a program that returns 0. How exciting. But let's keep track of that 0, because as we start making our transformations of the program, we want to make sure that we haven't changed the meaning of it. And so 0 is nice and easy to identify and recognize. And we'll start from this position. So here's our program. Now, what I'm going to do now is start removing some useful abstractions that the C# programming language and most other high-level languages afford us, and working my way down back to the raw level, the bottom level of the machine. So let's start by removing the capability of combining complex expressions. That is, I'm going to disallow this nesting of functions or expressions that we have here. Instead, I'll be requiring that all computation has to be done on a separate line and only one computation is allowed in one line, on each line. So this computation here, which is a sum of two products, would have to be divided up into two pieces. And in order to correctly evaluate the expression, I first have to evaluate 8 times 3. But then that needs to go someplace. So I'll create a variable t1 to store that intermediate value. And then I can similarly store the product of b times c in a second variable. And now that I have both of these products computed, I can now add t1 and t2. And I'll put the result back in t1. So I'll say t1 equals t1 plus t2. And then finally my result is going to be t1 minus 1. So these 4 lines of code should give the same result as this one line of code that I had before. With this new restriction, you can only perform one computation on each line. All right, let's try and see if that retains the value of my program. And it sure looks like it did. So I'm satisfied with this. I can now move on to the next restriction, or removal of abstraction. I'm now prohibiting the usage of general variable names. I'm going to enforce a strict naming convention that every variable has to be called x followed by a digit. So I'll rename this x1, and I'll rename this x2, x3, x4, x5, and finally x6. All I did here was rename the variables, right? So the program should not have changed meaning. Let's verify that before we continue, though. Indeed, we still get 0, so it appears as if we haven't changed the meaning of the program. So I can go a step further. I can say, well, look at all these variables named x. They all look very similar, and in fact, we could rewrite the program so that instead of referring them as individual values, I'm going to store the storage for these variables in one array. I'm going to call it x, and I'm going to give it a size of 32. So in this array, I can store 32 integers. And then what I'll do is I'll replace all these variable references with array references. So I will replace x1 with x index 1, x2 with x index 2, and so on. And then I will have to remove these declaration or the integer declarations because now they're no longer necessary. Okay, let's try and verify that this still is giving the right result. Still giving 0. Cool. So our program now is accessing values only out of this array. It's initializing some values to initial values and then performing some computations, leaving the result in slot with index 6. Okay. So how can we then go down deeper? Well, one of the things that we could notice here is that there seems to be an interesting regularity here. These first 3 instructions, they are just assignments, basically, just storing these 3 values, while these other 3 are binary computations. We have a left side and a right side. And in some of these computations, we are multiplying or adding, we're subtracting, but also notice that in some places we are using a register value on the left and a constant value on the right. While on the others, we're multiplying two numerical values together from 2 slots in our array. So there's this distinction between these 2 modes, so to speak, where in some cases we're using an immediate value, in other cases we're using another array value. And this becomes important in low-level programming. In machine code, these instructions multiplying by a constant and multiplying by another variable are actually represented by different instructions. But at this point, what we have here now is very, very close to machine code. It's just that it's still written in C#. And so what we want to do now is move even closer to the machine code of a Risc-V CPU. And to do this, we're going to introduce an abstraction in a sense. We're going to change the way the code looks like so that it looks more like a low-level machine language does. So what I'm going to do is I'm going to, instead of allowing these free-form infix operators like multiply or plus or minus, I'm actually going to replace them with a word function call. So I'm going to call this add or multiply, and I'm going to just use the word mul. Whoops. And so we'll do something like this. And then add will be another function that will take 2 parameters. Actually, why am I doing add on a mul? I'm not paying attention here. This is another mul. Now this is an add. Visual Studio Code is getting in my way here. Okay, and then now this you could say is an add or subtraction, but I claim it's an add. I'm going to express this as an addition of a negative number, which is fine. You're allowed to do this. So now we need to write these functions. Let's write them. So we'll write the multiplication function first, which is easy. It's just x times y. And then similarly for the add function, like that. Now if I didn't screw anything up, we should still get 0. Let's give it a try. Awesome. So the program is still computing the same value as before. Now though, all of those operations that we saw have been replaced with function calls. Now, what we could do is take this a little bit further or closer to the way this is done on a machine and say, instead of having these functions take 2 arguments and returning a value, what they're going to do is they're going to take the return value and instead of returning it as a function return value, they're going to mutate a new first operand or argument. So I'm going to say the multiply operation will take as its first argument a ref integer. Now, for those of you who are not familiar with the C# programming language, what this means is that rather than passing in a variable by value, what we're doing now is we're passing in a reference to the variable, which means that we can write this instead. I'm also going to change this function to become void. So now, this function, instead of being called this way, we're going to pass in x bracket 4 and x bracket 5 by reference. And in C# you have to show your intent by specifying ref. So here I'm saying this x4 is going to may get mutated by the mul function. I'll make the same change here for the add function. And now we need to make sure that the add function takes a ref All right. Well, let's see if we've changed the behavior of the program. And it appears that we don't. Okay, great. So another thing that we're going to do is we're going to disallow these simple assignment operations. We're going to insist that these assignment operations have to be carried out using add. And you might wonder, well, how's that going to work? How do you add? Well, what you could do is decide that if you add 0 plus 3, that's the same thing as 3. So if we had one X register that contained a 0 at all times, then we could change that to this. And now we are assigning x0, which, since it was just created and was filled with zeros, is still 0. And we're going to add 3 to that. We get the number 3 as expected. And same thing here, x of 0 plus minus 4. And x0 plus 2. And we'll use the same syntax as below. We'll say add ref, add ref, add ref. And then let's get rid of these equal signs. And let's see now. Yes, we need to get rid of these plus signs as well. We're removing all of this high-level goodness and moving further and further down. So now we have a program that if I run it, should still give 0. Great. So if you look at this program, you'll see a lot of repetition. There's a lot of X bracket thingies going on all the time. So you might start thinking, well, isn't there a way we could reduce the duplication that we're seeing here? And sure there is. Well, one thing you could do is, for instance, the function mul and add, they could be passed indices into the register, or the X array. So instead of passing in the value of x1, we could just pass in the 1, indicating that we're interested in the value of the register, or the array at index 1. So we would change this statement here from what we see before to just add 3, 0. But then we run into a problem. This 2 here, it's not clear whether that refers to an index in the array or the actual immediate value 2. So what we'll do is we'll introduce a new function called add immediate, or add I. What this will do is it will take the slot, or the value in slot 3, add and replace it with a value that results from adding the value in slot 0 and the immediate value 2. So this would result in 0, which is fetched from x of 0, plus the immediate value 2. So this is different from the addition that is going on down here, where we're fetching both the operands of the addition from the register array. So what we'll do is we'll replace this with a 4, 4, 5, I'll comment this out. And we'll just go systematically through all these and do these replacements. So this becomes an add immediate. And we'll pass in 1, 0, 3. Remember that the second operand, or the last operand, is going to be the immediate value. Let's comment this out. And then here we'll say add immediate. And we'll talk 2, 0, and -4. We did this one already. Let's write an add I function while we're at it. So this will be the destination index, and then we'll have the source 1 index and the source and the immediate value. So we'll do destination gets the value plus the immediate value, like this. Why are we not happy? Let's change that to void function so we can refer to this array over there. Okay, now we need to change add to conform to the same pattern. So instead of references, we'll have destination index, source 1, and source 2. And we'll do the same thing here where we say x of destination equals x of source 1 plus x of source 2. And here in our multiplication, we'll need to introduce a destination and a source 1 and a source 2. And let's get rid of the static. And now we fix this. So now we no longer need to index these. And it looks like we need an immediate multiplication. So let's make sure we have one of those ready. And this is an add immediate. So there is now a need for a multiply immediate, where this is not a source, but an immediate value. This should be a multiplication. And this should also be a multiplication. All right. So if I've done this correctly, the program should still compute 0. Let's see if we can verify that. Still computes 0. That's amazing. Now if you look at this program, you'll notice that it's becoming harder and harder to understand what's going on. We've lost a lot of the flavor of the high-level programming language now. All we have are these function calls. But we can make this even more primitive. What we could do is say that each one of these functions is actually just a selector. It's selecting a particular kind of operation. But we could make, instead of having multiple function calls, we could make these be 4-term calls to a function that we're going to call exec, maybe. We're going to call exec, and we're going to define a bunch of constants. I'm going to define a constant called add_i, which is 1. And then I'll define another one called muli, which is 2. And then we'll have a regular add, which is 3. And finally, a regular multiplication, which is 4. And then what we'll do is we'll replace these calls to a single function where we're passing in the kind of operation that we want. So it's a little tedious, but we'll get there. So now what we need to do is implement the exec function. And the exec function is basically going to be a big fat switch statement where we take an operation as the first parameter, and then a destination and a source 1 and a source 2. And then what we do is we switch on the operation. That is, if it is an add, actually let's just use the functions we have. So if it's a MUL or multiplication with 2 register or 2 array operands, we'll just compute this and then a break. And if it's a multiply with an immediate, we'll generalize to this. In the case of an add, we do this. And in case of an immediate add, we do this. Great. So, we have to handle the case when it's an unknown instruction. So for now, what we'll do is we'll throw an exception. And we'll say instruction or operation not implemented yet. And let's do this syntax. Okay, great. That should fix it. And what happened? There we go. Let's save that. And let's type exec correctly, and let's run it and see what happens. Okay, great. So what we have done now is continue the process of making this program harder and harder to understand, but closer and closer to what actually goes on underneath the hood of a modern CPU. So there is this function called exec, which takes us an operation and 0 or more operands, in this case 3 operands. The first one is the destination of the computation, and then the 2 other operands are the values that we're computing on. And as you can see, it's just trundling along and performing a computation, even if it's expressed in a very, very primitive manner. But we can go a little bit further than this. We can say, well, here we have this exec being called multiple times, and I'm sure we've all learned that if you're repeating yourself, it's time to maybe write a loop or something. But if we're going to write a loop, we need to have something to loop over. And in this case, we'll probably want to create an array of instructions that would indicate what we want to have executed. So maybe we'll define a new type called instruction. And this new instruction will take a destination and a source 1 and a source 2, and we'll store them. And let's create those member variables. I'll create them as publicly readable fields. So now we can create an instruction. So now we need to create an array of these beasts. So I'm thinking, let's call this array, well, let's build it in a list. So we'll create a list of instructions. And then we'll just add these to our list. So let's just add, well, add is not a good word. Let's call it assemble. Let's assemble our instructions one by one. So I'll grab all these. And then I will replace the word exec with the word assemble or asm. And then what this function will do is it will, let's just write it. What it will do is it will take an operation and the 3 operands and build an instruction and add it to our list. Simple as that. So like so. So here, my little program, I'm saying assemble all these instructions into my list of instructions. And then I no longer need to execute them like this. Instead, I'll just say for each var instruction in instructions, execute the instruction. And so this, instead of taking 4 parameters, it now takes an instruction. And then we'll say inster.operation. And to save some typing, oh, I called it opcode. We will change dst to inster.dst, and then we'll change src dot to inster.src. And then there we go. So to review, what we did was we assemble our instructions, and then once they have been assembled, they're placed into insters. I'm going to call this program, actually. That makes more sense. I have a little program consisting of instructions. I assemble them, And then once I'm done, I execute them. Let's see if this still works. Indeed it does. So this incredibly crude little program is actually an example of two pretty important concepts in low-level programming. The first part is this part. What we're doing here is assembling the program, assembling these instructions from these parts. And what I'm doing is I'm combining the operation add I with the three operands and putting that into an instruction. And then on the second half of this program, what we're doing is performing the execution of this program. This is the beginning of an emulator. Because what we're doing is we're reading in instructions from our program one by one, and then we're executing them. So I'm going to stop here, but I invite you to think about what could be our next steps here. One of the things we want to do, of course, is make this program a bit more interesting. Right now it's limited to only 32 variables, not even that, 31, because we're reserving slot 0 to always be 0. But we want to access a lot more than just 32 integers. We want to access megabytes of memory if possible. And also, more importantly, there's no way to repeat operations. There's no way to create a loop. There's no way to make decisions. And without that, we can't really say that we have a fully fledged CPU. So in my next session, I'm going to be continuing on this work, and we're going to make this program start looping and start reading memory. Until then, thanks very much for listening, and have a good one.